Okay, so welcome to my expansion on Chapter 7 for my Introduction to Automation course. This is an expansion on Chapter 7, Automation Made Easy, which is a book that I think falls short on the data collection and machine learning topics, even though it does talk about optimization. What I'd like to do is break this down into three separate areas. The first area is data collection. You can't optimize anything until you know what the value is. You have to calculate somehow what information needs to be collected and then how you're going to optimize the usage of those particular parts of the factory or resources or raw materials. You have to figure it out by collecting data. And data collection is one of the key values of mechatronics of an automated factory. In the old days, guys used to data collect by pulling up big sheets on a clipboard, and they'd wander down to the factory floor and they'd stare at an operator with a stopwatch and scribble down notes. And that was considered a very important task, and it was really the only way to be sure you knew what was going on the shop floor. And that's changed. That's changed a lot. The second piece we're going to dive into is optimization. I'm going to speak about it in a much broader sense than the book did, so we'll go into that. And the third piece is machine learning. Machine learning is where you would use data collection, and machine learning and the application of machine learning is the ultimate optimization. You have the ability to use lots and lots of data points to collect them and do the analysis to figure out how to improve your factory floor. So let's dive into this. The first step is data collection. This is the biggest value of you guys as your shop floor automation experts. The guys that you guys are all training for roles like this, where you're initially a technician and eventually more of a valued engineer and maybe a programmer, and maybe you're doing this all over the world, depending on what career you pick. But you guys are going to be doing the data stuff. And even though a lot of what you're doing is programming the automation piece, you will also be collecting data as well. And that data collection has extreme value. A lot of companies right now are struggling with this. So let's start off with, first of all, how do you collect the data? What are the integration points? And what methodologies do we use? And so I'm going to talk about a few different methodologies. The first one is smart machines. Many automated machines out there have computers. They have actual microcomputers. They have PLCs. And they may have industrial, actually full-blown industrial computers built right into their, right inside their housings, right inside of their enclosures. You've got a smart machine with true programmability, and that smart machine has lots of sensors built right into it, and it can collect lots of data inside that smart machine. But then, what do you do with it there? And where can you take advantage of that sensor data? That's the next step. Obviously, collecting data from a smart machine requires an interface to that smart machine from your perspective as the plant owner, or the plant manager, or an automation expert at the plant. You want to have a connection, and a lot of times these smart machines provide you that connection. They give you the ability to communicate to that machine over an Ethernet cable or over some other means to collect that data and pull it into your plant-wide database. So we're going to get to the database in a minute. Another classic way of collecting data is PLCs and sensors. Now, this is the kind of the core of the mechatronics course, the idea that mechatronics uses programmable logic controllers and sensors hooked to those programmable logic controllers, and we collect that data into these PLCs, and the PLC data is then used to run some portion of automation in the factory. But many factories don't take advantage of this data once it's stored in a PLC. It just sits there. And what's more, there's no history. So how do you take advantage of PLC data? Number one, you have to store it in a historical manner. You have to be able to record that sensor data over time, and you have to find some way to pull that data out of the PLC and put it into a plant-wide database. The last, and actually growing in popularity, means of collecting data from the shop floor are microcomputers. These little bitty computers, you've heard of something called a Raspberry Pi. It's a little $5 to $10 computer, very, very inexpensive. You can buy relatively cheap sensors to hook up to these little inexpensive computers, and then you can set them up on a network. So now I can inexpensively, without any other automation in my process, collect data. I can collect temperature data, I can count parts, I can collect image data with a Raspberry Pi and a camera. I can collect a lot of information and then store that somewhere. So the first question you might have is, why? Why would I want to collect data? And that leads me to my next topic, decision point. What data do we want to collect and why? And let me tell you, right now, manufacturing facilities, at least all the ones I've been involved with, have really struggled with this. The old school guys are like, they want to go out there with a clipboard, just like I first mentioned. They want to be out there with their clipboard, looking over the shoulders of their operators, making their operators nervous, and collecting the data the old school way. They want to post that data on a big board behind that manufacturing area using whiteboard, or Sharpie if they're feeling really, strong about a particular data point. And they want to have sort of this process that's based on 1970s or 1980s methodology, which is all manual. So the question is, how can I collect data that would be a lot better, a lot faster, and why am I collecting data? Let's just say you are a manufacturing facility. Let me give you one example. You are a manufacturing facility that makes a part that is going to be used to crimp the lovely electrical crimp connector that's used in an automotive environment. Let's say it's being used by Tesla to hook up their battery to their main drive motor. And your crimping tool has to be exactly right. If it's too small, it'll overcrimp, and that it'll crush the little wire, or actually the very big fat wire between the battery and the motor, and that wire being crushed will mean you have high current, and then that will fail too early. Or let's say it's too loose, it won't crimp it quite tight enough, and now you have a loose connection between your wire and your motor, and slowly over time that loose connection will build up black stuff, some oxidation, and it'll slowly increase in current. You have much too much current, and then it'll blow the motor and or the battery, and your Tesla will fail too early. So you can't have either one of those. So how do you optimize your machining process to make sure that each crimping tool is exactly right? Well, it could be that as each crimp tool is produced, you take a picture of it, and you record all the process parameters around that image. Let's say you took a picture of that crimp tool, and then you recorded the process parameters of which raw material you used. You record how long that machine was running, how fresh the cutting tool was that cut out that particular crimping tool. You recorded how much current was used by the motors that ran that machine that cut out that crimping tool. You record all this other data. You might even record which operator was on shift. Which shift were you? Second, third, weekend shift, first shift. All that data can then be recorded with that image of that crimp tool. So then, let's say 6 months down the road, Tesla complains, guys, I had a car fail too early. We think it's because your crimp tool was off. Even though it initially met specs, it failed. So now, 6 months later, I can go look at all the data for every single crimp tool that followed that same exact image. In other words, the image matched, even if it was within specifications of the final product that Tesla required, It may not be exactly perfect. So I could take all the images that match that failed tool image and connect them to all the data that associated with that tool failing, and I can do the analysis to figure out why that tool failed. Was it the wrong material? Was it the wrong operator? Was the cutting tool that cut out that crimp tool too dull? Was it too much power was used to drive that cutting tool, so therefore it may not have been dull, it may have been a different issue? I have all that data now that can be used to find that solution and make sure it never happens again. So then I can say to Tesla, man, we found the problem. Here it is. It's never going to happen again. And you can do that almost right away if you have all the data then to do your analysis on. So that's an example of why you would collect data. And there's a million examples like that in the factory floor. A lot of them are having to do with solving quality problems, but then there's many other ones as well. If I have real-time data and how much that product costs to make, then I can use that real-time data to determine a better price for the product. I don't have to rely on average cost. If I have real-time data on all the different operators, and I find out that one or two operators are creating a larger amount of problems, I'm not going to fire them if they're good operators. I'm going to want to retrain them, and I can get to the root cause of why that particular problem has occurred and train that situation, or maybe even put a mechanical fix in so they can't do that thing anymore. So this is why you want to use data collection. It is a critical aspect of the manufacturing floor. Finally, when it comes to data collection, you have to store it somewhere. And you guys are all familiar with your PCs. You know you've got hard drives in your PCs. You probably also know that it's easy to store stuff on a hard drive and never find it again. So you really need to know what you're doing when you store things in your hard drive. You need to have file folders where you can put things. The same is true for the shop floor. I can't tell you how many times I've seen data collected in a manufacturing facility and never used again, or so disorganized storage that there's no way it's of any value. One plant that I used to work in that shall remain nameless, when I started learning their database structure to use for my optimization tools that I was creating, I literally found that I had access to thousands of separate databases, all with different naming schemes, none of which matched, for which there was absolutely no description anywhere on what was in any of these databases. In that case, the only way you could figure out what was in a database was the extremely highly valuable guys who really knew that stuff. You hope they didn't quit, because my goodness, their knowledge was absolutely required for any understanding how the shop floor data was collected. So you have to pick the right data, and then you have to store it in a logical, well-documented facility. You have to decide the value of that data is very high, and you have to make sure it's a managerial, we'll call it imperative, that we keep good trained personnel and that we train personnel on how to use the data, and that data stays around. Obviously, storage capacity is an issue. You want to make sure you have the right storage capacity, and you have to have the long-term training in place to make this data valuable. It's useless to collect data if you never use it. So then the second topic of my view of this is the optimization. Optimization falls into two basic categories. I call it the micro and the macro. We already talked a little bit about the micro in chapter 7, and that is the idea that you have individual manufacturing processes, the actual control loops, where you would optimize for a particular condition. This really isn't what I'll classify as optimization at the plant level, and not really what the course is about, but it is important to understand how to do these things. It's less important overall because I can buy a $100 microcontroller that'll do this just fine automatically for 90% of my applications out there now. No longer important that you guys as automation technicians need to be able to tune these loops, but you need to learn about them in future courses here in mechatronics. You will learn about them. At the macro level, This is the large picture. You've got to have optimization for material usage, for resource usage, and financial optimization. I think I've touched on all three of these already. Material usage is like I've got a stick of framing material for my windows at Pella, and I want to optimize my production orders in sequence so they maximize the usage of that framing material and minimize the short lengths lying around my facility. Resource usage is I want to optimize the resource, say, of a manufacturing facility or of a particular work cell to make sure I've chosen the right products to run on it to optimize its financial value to my plant. And that links to financial optimization overall. What should I be running in my plant and why? If I have products I can run in my plant that are going to make that plant more highly valuable, even if it's not traditionally what's been run in that plant, I should be able to figure that out. And there's a lot of tools for optimization. The book, chapter 7, talks about some basic math. Excel, and there's actually extensions to Excel. This is the Microsoft Excel tool that help you optimize based on data sets. And there's some excellent tools out there. As well, there's a lot of custom software and specialized software, like one of my favorites, a specialized software called R, which I can program in a very basic way. There are a lot of specialized optimization softwares out there. Don't be confused by them. They all have different value, different usage, and different experts. Finally, we're going to talk about machine learning. Machine learning is where it's at. This is the newest thing, probably less than 10-year-old overall technology, but it has exploded into the manufacturing world as well as a lot of other worlds. And I've added some links here to this presentation. There's also some links in the D2L site, which are the same links, so you can go view these links. But what is machine learning? Machine learning is the ability to take data sets, and by data sets, I'm using it very broadly because in some cases, a data set might be an image or multiple images. And based on those data sets, I should be able to create basically a decision tool. So for instance, if I have a data set which says all my good parts for this crimping tool fall into this data set, and then I've got this handful of bad parts that I produced, and I've got a whole set of data around those bad parts, I should be able to run all that data set, all those good parts, and then the handful of bad parts through my learning tool so that anytime on the shop floor, the instant I produce a bad part, or when I start trending towards the conditions that led to that bad part, I should be able to say, whoa, stop the manufacturing. Let's get this fixed. Start aligning yourself differently, change the conditions because we're heading towards that bad part. That is the essence of machine learning. It is the ability to take a data set and make decisions based on learning what good parts are and what bad parts are. What's the value of this? Well, it's huge. In the medical industry, they are using images of cancer cells to help determine whether a quick snapshot of your weird little bump you've got on your arm is cancerous or not. And what they found out is that machine learning is more accurate than doctors on average. In fact, a lot more accurate than doctors on average. And that is just one tiny application, relatively recent application they came up with to prove the machine learning works and really works well. So it's hugely valuable. It helps you reduce costs radically in terms of quality. Also, it might help optimization costs. Also, it can help with any number of particular applications in the factory. It's a huge cost savings tool in the manufacturing facility. It's really, really important in the long run. So that's the end of the value. Obviously, it saves money and lives if we're talking medical. So let's talk a little bit about the tools out there. Data set learning. Data set means I have a bunch of data, like, which operator, what shift, what machine tool, what that if I have a data set and I link that to a condition, good part, bad part, that's information that I can use to create learning around data set. Image learning, that's another classic one. That's the one we talked about the most at the beginning, about taking an image of cancer cells and learning whether or not they are cancerous. And then you've got unrelated data connections. Sometimes you can create data sets based on timing or some other factor that seem unrelated. You might be measuring light levels, you might be measuring air temperature, you might be measuring any number of factors that don't seem related when you connect them. But when you run them through a machine learning tool, you find out that there is some potential connection. One thing that machine learning tools are very, very good at is looking at broad sets of data and then running through analysis to see if there is a relationship between those sets of data. So that's pretty much it that I want to speak about machine learning and this particular chapter, optimization, data collection, and etc. I would urge you guys to go to these links I provided, watch them talk about skin cancer and some of the huge things they've done with image recognition. There's a couple links to factory automation and machine learning and that sort of thing. They are really interesting, so I will urge you to go into and check them out.